Okay, I think we can get started. Ines, if you want to go ahead and introduce yourself.
All right, thanks. My name is Dennis Afkin. I'm a research scientist at Johns Hopkins in James Taylor's lab. And I've been with the Galaxy project for nearly 5 years in various forms, I guess, and mostly working on leveraging and sort of advancing cloud computing and how Galaxy uses the cloud to make it more accessible. So this talk today, I kind of want to talk a little bit about some of the stuff that's been going on for the last 6 months to a year, and mostly an engineering effort of trying to assemble a few things that have sort of to some degree developed independently of each other and have come out to yield pretty cool results. And so some of this is sort of in beta, so we're going to stick to slides, and then if you guys try this out or have any questions, we are working on this kind of stuff. So, all right, so inevitably, there's always a person or two that doesn't really know or hasn't seen much of Galaxy. So just a couple of minutes on what Galaxy is. So the Galaxy project's been around for nearly a decade now, and it's primarily focused around the Galaxy application, which is a data analysis and integration tool. And what that means is it has a capacity to take any command line tool, and by providing an XML wrapper for the particular tool, its inputs and outputs and so on, it integrates with the rest of the framework and other tools that are available within the application. And so from the user standpoint, command line tool has now been converted into a web app, and it allows one to take the outputs of one tool, feed them into the inputs of the next tool, create workflows, share things, and basically advance both reproducibility and transparency of computational science. It has primarily been used and it's focused on sort of genomics and bioinformatics maybe more generally, but there's been applications in other domains because, like I said, any tool, command line tool, can be wrapped and made available in the context of the framework. The next thing is it's a free for everyone web service, so an instance of the Galaxy application running at usegalaxy.org provides access to roughly 150 tools, several terabytes of reference genome data, and every user gets a quota of 200 gigs of persistent storage, and of course computes to go along with it. And finally, it makes it possible to be extended in ways that we are either haven't foreseen or don't put a lot of effort towards. So anybody that's interested in extending it, of course, is more than welcome to do it. So now there's three different ways to kind of get access to Galaxy, and I'm going to use this as a segue for what the title says and what we're going to spend the rest of the time talking about. So most notably, at usegalaxy.org, there's an instance of the application with all the stuff that I said in the previous slide available. And so that's by far the easiest way to get access to one. So register, log in, and persistent access, compute capacity tools, everything pre-installed. And because as I said, it's open source, a lot of people, namely 60 plus other institutions and labs, have decided to take Galaxy in some way, make it suitable for their use case, either by publishing tools that they have developed or tools that they use or more capacity. And they came forward and made it available to the rest of the world, just like use Galaxy. So that's one extreme. So you have dozens of public Galaxy servers that you can use. The other extreme on the right-hand side of the slide is you install one yourself. So the two commands that are at the top of that box on the right is all that it takes to install Galaxy. So download and run, and things will start showing up on your screen. Getting it ready for the production environment is a little more involved. It takes interact with a proper database and just various sort of config options that you want to choose. And so to make that a little more streamlined, we've been developing a set of Ansible roles and playbooks that make this even more accessible. And so a lot of the stuff that has to be repeated for every public server it has the potential of now being automated. And Galaxy ultimately sort of acts just as another client to any kind of or a range of distributed resource managers. So whether you run it on your local laptop or on a cluster or on supercomputers, we'll see it's just another client, and it interfaces with a range of those. And sort of wedged in between these two extremes of how you access it, there's Galaxy on the Cloud concept and the CloudMan application that we've developed that takes all of the sort of cloud intricacies and stuff and creates a platform, a virtual cluster basically that runs Galaxy in a production like setting. And so we've had this going and running or available for the better part of the last 5 years on Amazon. In the last 2-3 years, it's also been available in the Australian National Cloud Nectar, and work is underway to make it available on the Google Cloud Platform in the foreseeable future. So that's sort of the in between the other two, as I said. And so what all of these basically have in common, and there's a bunch of compute capacity that's hidden behind various installations and various incarnations of the application. So the map of the U.S. here actually shows what happens at usegalaxy.org. So a couple of years ago now, or nearly that long, the Galaxy main has moved from being hosted at Penn State to being at TAC, and there's a dedicated cluster, and recently there's been sort of some work that I'm going to talk about here, I guess, is how you actually leverage some of the more distributed resources in addition to a dedicated cluster using the Rodeo Cloud, the Stampede supercomputer, and then a couple more external resources. But other institutions also have access to their own clusters. People have access to their own workstations. There's, of course, the cloud that comes up with a lot of machines and so on. And so the idea behind the work that we're trying to do is kind of link all this stuff up. And if there's machines that are available, why not make it simpler without people actually having to do a lot of the manual effort? So, and the driving force, I mean, the motivation example for this is that as things currently stand, every instance of Galaxy is configured in a fairly similar manner, in that there's the application, there's some kind of database, there's installed tools, reference data, of course, the compute to process all this stuff. And then they primarily differ in, of course, the compute capacity, but also, so from the end user standpoint, in what service, what function they serve. So whether they have one tool set or another tool set. And so from the user standpoint, Galaxy is great because it hinds the command line interface to a bunch of tools. It allows you to connect them and all this. But then at the sort of next level up, if you want to connect tools that aren't available in one instance of Galaxy yet are at the other, it's up to you to make sure that you have an account on that instance, that you actually have data available, that you've transferred your past different instance and so on. And so it sort of produces this discomfort and annoyance, I guess, at best. And so the idea is to sort of integrate all of this and provide a more focal interface to Galaxy that allows you to connect to one Galaxy, and then depending on the resource capacity, depending on the available tool set, where the data resides, the system itself will sort of choose where to, in fact, run the job. And so this is the big picture that we're trending towards. It's quite far, actually, from being realized, but that's the basic idea. And so one aspect of this is things that I'm talking about for the rest of this is sort of the cloud bursting, and how can we leverage things that have been developed over the last year or two to make cloud bursting happen. And of course, there's a number of motivation scenarios that kind of overlap with the general cloud systems. So, we have peak usage scenarios to be able to burst out. People have departmental clusters that they occasionally need, they have a workshop or they have a deadline for a proposal or something. And then, of course, you want to be able to use more capacity than resource heterogeneity a lot of times. De novo assembly is a good example of a process that requires a lot of memory. And so instead of maintaining those machines, let's just grab it from the cloud. Software licensing issues where software can't move. If you have access to a department cluster, but it's either a bit dated or you don't have enough permissions to install some kind of library that you might need or a tool may need, you can leverage the cloud. More and more people are getting merit access to the national cyber infrastructure, and so being able to leverage that at the sort of individual users level, which is the ultimate goal, or even at the project level. So these are sort of the big picture of what we're really trying to achieve, the motivating factors. And so if we translate this into things that we can actually that we can react to, we can talk about sort of the notion of burst triggers and essentially decide, when do I want to burst and where do I want to burst. So theoretically speaking, you can, again, kind of the flip side of the previous slide is the resource capacity is inadequate, maybe then. If the requirements for a particular job state that I need to use a specific machine, good. With data locality, some of the sequencing data centers are depositing data in various forms of cloud storage. So instead of having to move that data, might as well just get to the goal of running stuff where the data actually is, and like then the system configuration. And maybe a user just has preference that they want to run something on a particular machine. And then on where do you actually burst, it depends on the resource availability. Public clouds, most of the time, I guess, enjoy the privilege of being virtually unlimited in size. Unfortunately, the academic clouds don't quite have that luxury, and so should be able to query a remote resource or a remote cloud and decide, do you actually have capacity? Do you have the instance types that I need for this particular job or not? And then decide whether this is the particular cloud you want to go to or not. And similarly with cost, if there's a budget, that makes things easier typically. Yeah, so this is kind of what motivation is, and so this is how we've realized this or assembled it in Galaxy, and it's basically a fairly straightforward three-component system. So Galaxy has this notion of dynamic job destination framework that allows you to choose where jobs should be sent. We have Galaxy Cloudman as a pool of resources in the cloud, and with a Pulsar service enabled. In the next slide, I'll say what Pulsar is, since I haven't brought it up yet. And then ultimately some kind of mapper function that decides which machine a particular job should be sent to. So we'll look at these in turn. So Pulsar, something that's been developed, sort of started outside of the context of Galaxy and now has moved into the Galaxy ecosystem, is a standalone job manager server for Galaxy, allowing you to, it handles the staging of data. Once the data has been transferred over, it submits the job to the resource it actually runs on, which is different from the resource where Galaxy itself runs. It'll monitor the job, and once the job completes, inform Galaxy that the job is completed, send the data back. And so it doesn't require what otherwise Galaxy requires is a shared file system, but it'll handle this job transition. And it's really a sort of convenient way of being able to leverage machines that you may not have complete control over, or just periodically use and so on. So really a really cool application that sort of integrates in with Galaxy. And so, like I said, we have three components. So the first one being the Galaxy Dynamic Job Destination Framework. That is it manifests itself as an XML file that allows you to specify job execution definitions and properties. So it revolves around two concepts of runners or plugins that define an interface between Galaxy and a job execution resource, such as basically being just run this command on your local system, or submit it to the Surian job manager, HTConf, or anything that's JAMA compatible. Of course, the Pulsar we just saw in the previous slide, and a range of others. There's probably on the order of a dozen runners interfaces that Galaxy implements. So you define which ones this particular instance of Galaxy supports in one part of that file. The other part of the file is the destination, so the resource and the job properties. So if you have access to a local machine, and you want to run jobs on it, you define where the job is actually run. If you have a DRM or something, say which queue you want it to go to, and depending on each tool, you may choose it to go to a different queue and so on. And likewise for properties for a job, how much memory allocation, what's the wall time, and so on. So that's essentially a simple XML file that gets set up, and you now have access to these machines. The next step, as I said, is actually getting access to some compute capacity, and the easiest one by far is using the Galaxy on the cloud. So we launch an instance that gets us a fully configured Galaxy application with a number of tools and an amount of reference data already pre-installed. And so that's sort of standalone Galaxy instance is ready to run jobs. Then we enable that Pulsar service that's been integrated into CloudMint. So we have this picture on here, this screenshot of CloudMint's admin interface or page that tells you what's currently running on a given instance. And so if you want to say, I want to run Pulsar as well, start that service from the UI, and you'll end up with a responding Pulsar server that then you just go back to step one, add it to the XML definition, and now you have a new destination for your local instance of Galaxy. And that's it. Now you've set up the link, you have the resources, you can turn on auto-scaling on CloudMint so that if it gets more jobs, it'll scale. When there's not enough jobs, it'll scale back and respond to the load. One thing to sort of keep in mind here, and goes back to both the motivation and the burst triggers, is the fact that tools, in fact, need to be installed on the machine that you're running. So because presumably, if you're using your own cloud instance, you have complete control over the system, you can just install it locally. So you can either use the Galaxy Toolshed to make, which is the Galaxy's version of the App Store for Galaxy Tools, and sort of install it, and then it'll become available to Pulsar and in turn the remote Galaxy. Alternatively, we can use Docker images. So you can wrap a tool as a Docker image, add that configured sort of detail into that step one job config file that we talked about earlier. And so when a tool is submitted by a user, Galaxy Pulsar, the whole sort of stream of things, will grab the image, the Docker image from the Docker Hub, make it available, run the tool, delete it, and send the results back. So one install applies to a lot of different locations. So a pretty cool thing. There's a sample use case for the Galaxy 101 on the web. This actually works in detail there. And the last piece of the puzzle is the job mapper function, which is basically the method of determining the job destination at runtime. So here's a simple one that's essentially a function that tests the just availability of the nodes on the current cluster. And if sort of circled in this orange box, if we don't have any available nodes, send the job off to the Pulsar job destination. And this is something that's been defined in that step one earlier. Otherwise, just default to the local drama runner. And that's it. I mean, you can get as elaborate or as simple as you want. You can define individual tools here. So if a tool is run on if a specific tool ID, if a job run using a specific tool is being submitted, send it to one machine versus another machine. It's any of the triggers that we talked about earlier, can be accounted for in this method and reacted to. And so but this illustrates a point of it being sort of relatively straightforward to do. And that's it. So I mean that's what should make this possible. It does make this possible. So as I said, dynamic job destination framework, the mapper function that decides whether you want to run local machines on any of the clouds that CloudMint supports, or for that matter, it doesn't have to be a cloud, or it can be just any Pulsar server that you set up on a local machine or remote machine that you have access to. And so, does it work? I mean, I guess is the ultimate question. And so this is this is a graph for usegalaxy.org. Since bursting has been enabled, it is a slight deviation from what I talked about in that bursting is not enabled via CloudMint side of things, but instead a direct Pulsar server. The reason it's not CloudMint is just because of the infrastructure and the way we have it set up. But the idea with Cloudman is that anybody can in fact do this on their own. And so the graph here shows that in blue we have the average job wait time, and in red we have the total number of jobs that have been submitted for a given week over the last what was that, about a year. And as you can see, in blue it spiked up to several hours of wait time before jobs would run, and since bursting was enabled late last year, it disappeared. I mean, we now are able to leverage Stampede with the Pulsar and able to just ship jobs off when there's more of them, and all that in light of additional jobs having been submitted, meaning higher throughput. So Galaxy Main currently runs on the order of 150,000 jobs per month, and yes, ideally with no wait time, I guess, for the users. And the other way to sort of look at this metric is because Use Galaxy is a public resource, we want to provide a really good service to the end users, the biologists, and so one of the metrics that we've been sort of Nate in particular defined and has been monitoring is this notion of a user frustration level, as the number of jobs that have been killed before they actually started running. So, a job sits in the queue, the user sort of after a while gets annoyed, and you saw on the previous slide, some jobs were sitting in for hours. And so, again, after this bursting has been enabled, we can kind of see at the tail end of this graph that the rate has gone to nearly zero. So, some pretty cool outcome and happier users. And that's all I have. As I said, this is primarily an engineering effort of assembling things that have otherwise been developed. So John Chilton developed the Pulsar, and Nate developed the dynamic resource mapper. I hooked it in with the whole sort of Cloudman side of things to see if this works, and apparently it does. So anyway, everybody else as well has done cool things. So I guess if there are any questions about this, as I said, the link to the slides is here in the documentation, and this is spread around. As I said, it's beta and very much under development, so we'll be, if there's interest, we'll figure things out a little better and make it more accessible over time.
Thanks, Ines. Are there any questions?
Yeah, hi, this is Mona. I have a question about the Pulsar, the job submission thing. You said it's a standalone tool, and so I was wondering, what's it written in, and how do you interface it with it if you're using it separately, with your own project?
It's an independent app, but it's Galaxy tailored. So the Pulsar is in some ways a specific version of Gram, if you're familiar with, from the Globus world. So it won't just run anything. It'll run Galaxy jobs. And the way it interfaces with external Galaxies or services, it has a REST API, or it has a AMQP queue or a messaging queue that you can set up and send messages that way.
Okay, so it interfaces with Galaxy servers only, is what it sounds like.
To my knowledge, at least, it hasn't been attempted with anything else. As I say, it has an API, so in principle, you should be able to have it take on jobs from non-Galaxy things, because just anything that submits stuff to that endpoint.
Right.
But it probably has some reliance on the concepts of Galaxy that I'm not sure that they would work in completely disconnected manner. So in terms of the data structures, I guess, as to how a job is submitted, for example, is probably one of the that it could probably be reverse engineered.
Okay. All right. Thank you.
No problem.
Hi, Ines. This is Nancy Wilkins here. I really liked your slides on the decrease in wait time and how that kind of directly correlated with users canceling fewer jobs and going away. I mean, I think it's sometimes hard to capture that user satisfaction level, and that's kind of exactly what we hope for in back-ending the high-end resources to, remove that wait time for gateways and serve more users, basically. So those were some very nice graphics. I hadn't kind of seen the results of the implementation of the Stampede.
Yeah, that is really yes, we're very happy. I mean, they're really cool looking graphs. So thank you.
Sean Doty had a question on chat. Sean, are you online, or do you want me to ask? I'll ask it. For bursting from local sites into the cloud, how do files get copied? Does it require a shared file system?
No. So that's the clear benefit of Pulsar, which handles data staging. So it'll literally just copy a file. And what the limits of this really are, I guess, is to be discussed and seen as we move forward with this. But no, it just copies the files, and so it does not require a shared file system.
Hi, Ines. This is Suresh at IU. So I have a question. So with this cloud bursting, so is the Galaxy is also still is this complementing XSEDE bursting at all, or is the Galaxy team focusing more on use the dedicated resources and then when there are more jobs, just burst out to the cloud?
I'm not sure what so this is it's two things, I guess. One is that Use Galaxy uses resources primarily at TAC for the time being, but looking at other destinations around the country as well to be able to burst and acquire additional machines depending on current demand, while most of it gets processed by the dedicated Galaxy cluster. And the specifics of sort of using the CloudMan side of things here is what anybody else or how anybody else can replicate this in their own environment. Because for Galaxy main, we use Pulsar directly, and it's been sort of a custom resolution or solution to make the bursting work. But so in order for others not to have to put in the custom development time, they can use the CloudMan concept and acquire additional cloud capacity like that.
Okay. So also a related one. So do you take advantage? Is this only Amazon specific, or trying to work? And also, I'm curious on if you are trying to take advantage of the Spot Cloud and things like that, or how advanced is the scheduling? Yeah.
So it's not Amazon only. It runs. So we officially support Amazon OpenStack, and in the future it'll be the Google Cloud foreseeable future, and then we'll see beyond that what happens. So that's that. And now the spot market and whatever is sort of embedded into the CloudMan thing because CloudMan is able to. It's able to leverage spot instances, I guess. So if one chooses to say, okay, I want to use spot instances, then yes, but it's probably a little less dynamic than you're envisioning.
Thank you.
Other questions? I had a question. I wasn't quite clear about the status. So obviously from the last couple of slides, you are using this on your main instance of Galaxy. But so is this, if I'm setting up my own Galaxy instance, I can also do all this, or is this code not yet available?
It is. So this is so the part that's so linking it in the form presented, meaning using the backend, the CloudMan as the cloud side of things, is waiting the next CloudMan release, which will have the Pulsar service enabled. So that's in testing. But without that, if you want to just have your own machines with Pulsar and a dedicated Galaxy instance that can leverage that directly, that's available now.
Great. Other questions? All right. Go ahead.
So this is Sudhakar. I was wondering if Galaxy hosts some of the public databases and supplies the data, or it is all users that need to supply the public data?
So by public data, what is hosted and available on specifically usegalaxy.org is a set of index reference genomes. So mostly, I think, coming from the UCSC. So that would be used in, for example, mapping steps and such. So that's one form of things that are used by tools, basically reference data that's been pre-formatted for its use with other tools. The other thing that Galaxy has is the notion of sort of shared or published histories, and would theoretically allow one to upload publicly available or shareable data and hence make it available to anybody else on that instance of Galaxy. So that's the extent to which sort of public data would be available. Galaxy as a whole doesn't host reusable kind of generic data.
So if it is going to burst into some cloud system, so the data has to be moved along with the rest of it?
So the input data, yes. Like I said, depending on the sort of the trigger that you choose to focus on, the data may already, the system is, I think, flexible enough that you could leverage where the larger data bits reside as to where you send the job. So that's I guess that's probably it. Yeah.
Other questions?
Yeah. I'm wondering on the Docker, like you mentioned, is the Docker mainly about is the Galaxy itself the whole installation Dockerized and shipped, or is more the tools used in Galaxy or Dockerized applications?
Both. So it's the context in which I was talking about it here is with tools only. However, there is a Docker image of sort of a production-ready Galaxy server running or captured in a Docker image or Docker recipe that's available. It was primarily a community-driven contribution that is being sort of encouraged and promoted and supported by the core team as well. But so if you want to get Galaxy in a Docker container, you can. But it won't come with all the tools. The tools will still be in their own separate Docker containers.
Can you share your experiences there, in it's on the running the Dockerized tools in the sense? I'm more interested in if there's a resource contention, if you're running all of them on particular VM or some resources, if one tool is seeking more resources, how transparently Docker is helping you there, and so on.
Well, the way I have relatively low experience. I've tried it out, done a few things, but I haven't put it through a really sort of heavy test. And the way that it's done is it becomes a job for the job manager. So the role of balancing the workload across the system that you're running this on is still left up in the hands of the job manager. So I guess you wouldn't be any worse off than just running a directly installed tool versus running it via Docker.
Other questions? All right. Thanks, Enos. And I sent out the link to your slides to the various XSEDE mailing lists, so everybody should have a link if you want to look at these on SlideShare later. And and also we will have Our next community call will be in 2 weeks on the 27th, and that'll be Andy Terrell from NumFocus. So this is a group behind a lot of the Python-based tools like SciPy and NumPy and IPython. All right. Thanks, Andy.
Thank you.
Okay. That's all for this week.
Bye.
Thanks.
Bye-bye.
Thanks.
Bye.
Bye.